And hello again, and my name is Tom Irvine, and I'm the instructor for this series of shock and vibration webinar units. And again, I'd like to thank the NASA Engineering and Safety Center, NESC, and Dr. Kurz Larson of NASA for making these presentations possible. So in our previous couple of units, we took a look at Fourier transforms, we looked at fast Fourier transforms, and every time we did that, we just took the transform over the entire duration set, whatever we had. Well, if we have a long duration measured time history, we have the option of dividing that up into segments. Then we can take a fast Fourier transform of each segment, and we can assemble the resulting segment FFTs into a three-dimensional plot, and it's going to be called a Waterfall FFT. And some of you may already be familiar with a cousin of the Waterfall FFT, which is called a spectrogram. So if you've done anything with speech and hearing or bird calls or wildlife acoustics, you've probably seen spectrograms before. So here we have a launch vehicle, and this is a suborbital launch vehicle. It's a sounding rocket. It is unmanned, and these are used for various kinds of NASA and scientific experiments. Typically, the launch sites would be the vehicles would be launched in Wallops, Virginia, or White Sands, New Mexico, or occasionally out of Alaska, or maybe even Kwajalein. So this particular vehicle is a Terrier Black brand. It's a two-stage, solid propellant, rail-launched, guided, fin-stabilized sounding rocket. And you can take a look at the YouTube video of this launch vehicle. And also you could probably just go to YouTube and type in Terrier Black brand. It's real interesting to see the footage of the launch, and there's actually some onboard cameras that make it real interesting. So one of the concerns about these launch vehicles, especially since they're long and slender, is that they have these fundamental bending modes. And you can think of this like a free beam undergoing a bending vibration. And these bending modes can be excited by high-altitude winds or aerodynamic buffeting, turbulent boundary layers, shock wave formation, thrust offsets of any kind, maneuvers, thrust vectoring. There's all sorts of different perturbations and disturbances that can excite these bending modes. And why are we interested in these the natural frequencies of these bending modes? Well, typically these are maybe 10 hertz or lower, and that is well below the expected natural frequency of our avionics and our circuit boards and our avionics boxes. So from an avionics point of view, in terms of the applied environments, we're just not that interested. However, just recall that these are guided vehicles, and there's inertial navigation systems on board these vehicles, and typically they would have 3 translational sensors and 3 rotational sensors. Those could be gyros, for example. And that set of 6 sensors, the intention is that they will measure the rigid body acceleration of the vehicle. But however, these launch vehicles also undergo elastic body vibration as well. So what we have to do as the structural dynamics or the vibration environments engineers, we have to predict ahead of time what the launch vehicle natural frequencies will be, and we need to convey that to the guidance and control engineers so that they can design their control systems with the correct stability for the various gain and phase margins or whatever they do with that data. And then once the launch vehicle flies, then we do our post-flight data reduction, and we have to determine what the measured natural frequencies were for the bending modes, or there could be more than one bending mode excited. Then we need to close the loop, and we need to go back to the guidance and control engineers and say, well, here's what we predicted ahead of time, which we already gave you. Now here's what actually happened in the flight. And that also gives us the chance, of course, to calibrate our models and improve our prediction techniques and to otherwise gather very important and useful empirical data. So what we're going to do is actually take a look at some flight accelerometer data from the Terrier Black brand vehicle. So we're going to go to Matlab here, and the main GUI package that we're running in this course is the vibration data GUI package. and you can download that from my blog as well as each of the data samples that we're going to look at here. So I'm going to type in vibration data, and this is up to version 4.3 and rising. So I'm occasionally finding bugs, and I'm also adding additional features and capabilities. So this will be updated for many revisions to come. So let's go ahead and we're just going to take a time history plot here of some flight accelerometer data. So we're going to go time history data, external ASCII. Then we have the Terrier Black Brant data. So here's the file name here. And then we have, let's see, it's acceleration G. That's going to be the Y unit. And then I'm just going to put flight data for the title. And so we plot this up. This is acceleration G versus time in seconds for one of the accelerometers aboard that sounding rocket. And what we have at the beginning is we have the stage 1 ignition shock, as well as the various launch acoustic effects. And then during the subsonic portion of flight right here, the vibration levels are pretty benign. And then the vibrations build up due to aerodynamic buffeting and turbulent boundary layers and shock waves, attached shock waves, as the vehicle accelerates through the transonic condition and reaches its maximum dynamic pressure or maximum Q condition. Now here at about 12 seconds or so, the first stage separates away, so there's a separation shock event. And then we have the stage 2 burn. So the stage 2 then burns till about 44 or 45 seconds or so. So here's our accelerometer data, and our task at hand is to go through this data and see if we can identify the fundamental body bending frequency for the vehicle as if it were a free beam. So I'm going to hit return here and leave plot utilities, and let's go to Waterfall FFT and Spectrogram. So I'm going to begin the signal analysis here, and we've got to, so let me read this first here. This script calculates the Waterfall FFT of a time history. The input array must have 2 columns, time in seconds and amplitude. The user may choose to perform the analysis either over the entire duration or over a smaller segment. So one of the decisions we're going to make is, first of all, we're going to decide, do we want the whole time history or do we want just part of the time history? And then if we decide we just want a smaller segment of the time history, then with our Waterfall FFT, we're going to subdivide that into smaller segments yet. A series of consecutive smaller segments, and those smaller segments they might be exactly consecutive or with no overlap, or they may have 50% overlap. So let's call in that Terrier data. So this is Terrier underscore Brant underscore 2 kilohertz. That's 2 KHC underscore LPF underscore X dot. Let's do the text file there. Okay. So it's going to be acceleration G, that's the y-axis. Oh, and then the time history pops up too. Acceleration G for the y-axis here. Now for the time history, we're going to have to make a decision. There's some relatively quiet period here thereafter where not much is going on, so we probably don't need to analyze that. So let's go up to about 44 seconds. And we'll go ahead and just start from 0. So let's go from 0 to 44 seconds for this time history. Okay, so I'm going to say 0 to 40. And I already know a few things about this data from experience, so I'm going to just put the frequencies from 2 hertz to, I'm going to put, let's put 48 hertz there. Overlap, we can do either way. We'll talk about overlap a little bit later maybe. And the next thing we have to do is we have to consider, how do we want to process the data? So there's our time history again. Park it off to the side. So we're going to have to subdivide our segment into smaller subsegments. And there's all sorts of ways we can process the data. And just to kind of simplify this a bit, usually it's good to kind of do an intermediate case. And typically I want to choose a Waterfall FFT that has about 40 or so segments. So I've got I got 2 choices there. I guess I can either be higher or lower than 40. And then we have the time per segment. And then we have the delta F, the frequency. So this will be the frequency step. Now a couple things you'll notice. This column of number here, this is all to the nth where n's an integer. So we're going to set up the data so it's to the nth where n's an integer so we can do our fast Fourier transform shortcut method. Now there's a big trade-off that happens. The smaller our segments are going to be, the time for our segments, the wider our delta F is going to be. Or the smaller our delta F is going to be for our frequency step, the longer our time segments are going to be. And in some sense, it would be good if we could get both of them to be as small as possible, but there's just a trade-off there. So let's see. For this case here, it is a bit of a trade-off. Why don't I go ahead and I'm going to do 30 segments, and that's going to give me 1.3 seconds per segment, delta F, 0.7629 hertz. So that's going to be case 12, or option 12, or row 12. And I'm going to go ahead and, I guess, use 50% overlap here. It'll make more of a smoother transition. So now that we've done our processing options, we've got our other parameters chosen. Let's go ahead and click on Calculate. Take a few seconds there. Okay, here's our spectrogram, and people that study bird calls and human speech and hearing, they love these, and some engineers love these as well. And I'm not really sure if this one is particularly useful for our case. But what you see along the y-axis is time in seconds, the x-axis is frequency in hertz, and then the amplitude is determined by the coloring here. So where the blue levels are, that's very low level, and where the orange and red are, those are higher levels. And what we want to look at is going to be more apparent in the Waterfall FFT, which is actually the format I mostly favor. So here's our Waterfall FFT. I like this a little better. It's more of a three-dimensional type plot. Okay, so we have our magnitude along the y-axis. Well, I guess that's the z-axis, I should say. We have our time in seconds, frequency in hertz. The magnitude is proportional to acceleration in g's. And we're not going to be very concerned what the absolute magnitude is. We're more concerned about what the relative magnitude is from peak to peak. So we're going to see a couple things with this data, and I want to first call your attention. We have some peaks that, well, let's just pick it up here about 10 seconds here, right before stage 1 burnout. So we have a series of peaks here, and they kind of go along this pattern shown here. So they start maybe down around 8 hertz or so, 8 or 9 hertz, and then they gradually the frequency of these peaks goes up to about 12 or 13 hertz maybe. So this series of peaks here is, well, that's the fundamental bending mode. And what happens during flight is the vehicle is expelling its propellant mass in the form of hot exhaust gas. Well, as the vehicle expels its propellant mass, the mass of the vehicle goes down, obviously, and the bending frequency goes up. That's again, natural frequencies are proportional to the square root of stiffness over mass. So there we've identified the bending mode frequencies, and that's important data to convey to the guidance and control engineers. There's actually another series of peaks at about 5 hertz, and what's going on there? That's actually, you'll see that the frequency isn't really changing as much as we can detect. So what's actually happening? This is a spin-stabilized vehicle. It's actually spinning around. And if you go to the YouTube video, you can see that the spin motion. And 5 hertz is actually the 2 times harmonic, the integer harmonic at 2 times. The fundamental spin rate frequency is actually about 2.5 hertz. And for various reasons, that's going to be a little harder to pick up on our data, partly because we chose 2 hertz as our starting frequency, and partly because the 5 hertz are more distinct. And in fact, while we're just playing around with this data, maybe I'll show you what happens. What if we try to actually get the spin rate frequency direct? So we have to redo our processing options, and I'll pick case 12 here. And maybe I should do case 13 so I can get a smaller delta F. 50% overlap. Spectrogram's not as useful as we might want it to be. So when we're doing waterfall FFTs, we kind of play around with the data. We like to change our processing options. We might play around with the time. We might play around with the overlap. And this is just another perspective. We've gone down to lower frequency and changed the processing option. And we can kind of sort of see these 5 Hertz peaks here. We can see the bending motion, the bending mode action as well. And down at low frequencies, we're actually picking up some kind of low frequency noise, maybe even some rigid body acceleration that might makes it a little harder to pick out the 2.5 Hertz action. But there are some spectral peaks occurring at 2.5 Hertz due to the spin motion. But more than that, the motion shows up at about the 2 times harmonics at 5 Hertz. And it could be that rotational spin rate is changing a little bit as well, shifting a little bit. But this is the sort of thing we do when we look at accelerometer data for a flight vehicle. So we're going to park the vibration data GUI aside here, and let's go back to our slides, our class slides. So this is basically what I showed you before, only here I have it at a PowerPoint slide. You can see the fundamental bending mode. It begins at about 8 Hertz, sweeps up to 13.2 Hertz as the propellant mass is expelled. And then we have the induced roll rate, the spin stabilization, which is the 2 times value is 5 Hertz, and then the true value is 2.5 Hertz. Let me say that again to make sure I said it right. The true roll rate is 2.5 Hertz, and then the 2 times harmonics is 5 Hertz. Okay, moving on to different launch vehicle. Now this is the Orion launch abort system. And this was an unmanned test, and the idea is this Orion spacecraft will carry astronauts, and it will be launched aboard some launch vehicle, maybe the SLS vehicle, or maybe even a Atlas V or Delta IV type vehicle. But anyways, there's a concern that during liftoff, or even before liftoff, or soon after liftoff, some emergency might happen. And if some emergency happens, then we want to have a way for the spacecraft to be removed from the launch vehicle and then pulled away to a safe distance by this launch abort motor. And so here's a test. This was at White Sands, New Mexico. And in this case, there was no launch vehicle. We just have the Orion spacecraft mounted probably to a stool near the ground. And here you can see the launch abort system ignition, and then ignites. And this main plume here is from the main launch abort motor. Well, there's also an attitude control system here. So there's actually 4 jets. You see the little smaller plumes shooting out horizontal with respect to the ground. And that's for attitude control. So during this test, the launch abort system motor, it's a tractor motor, it pulled the launch vehicle, the spacecraft off the ground to some safe high altitude. And then eventually the launch abort motor system separates from the spacecraft, and then the spacecraft has its 3 parachutes, which deploy so that the spacecraft can make a soft landing on the ground, with the idea of saving the lives of the astronauts. So this was an unmanned test at White Sands, New Mexico for this system. And here's just a diagram. So we have for the pad abort test, there was a boilerplate crew module, aero closeout, an adapter cone. The raceway houses electronic cables, the abort motor here. And then it's interesting, these 4 nozzles for the abort motor, this requires a thrust reverse because the or I should say a reverse of the exhaust flow. So that's a real interesting. So it's acting like a tractor motor in essence, and so the combustion cavity would be probably a longitudinal cavity as shown here. Exhaust gas go forward, get turned around by each of the 4 nozzles, and directed outward. Another interesting thing that happens is there's different types of plume impingement effects that occur on the raceway adapter cone and the spacecraft itself, and that's a whole other analysis to look at the high-intensity acoustics from that. There's actually 3 sets of solid motors on this vehicle. The main motor here is for the abort thrust. There's the attitude control motor, and that puts out those 4 plumes that you saw in the previous photographs. And then after the launch abort motor completes it's burned, then the jettison motor kicks in, and this whole launch abort system is separated from the spacecraft, and then the jettison motors push it away or carry it away for a safe separation at the proper altitude. So we've got some data from this launch vehicle, and you can actually pick up this data from the Vibration Data blog. And I'll just go ahead and show you here the Waterfall FFT. So this is our Waterfall FFT from our launch abort system. We've got the magnitude. It's proportional to acceleration g. Again, we're not concerned what the absolute magnitude is. We're just concerned about the relative difference from peak to peak. Yeah, if we need the absolute magnitude, we can get that other ways, just by looking in the time domain, for example. We've got time in seconds, frequency in hertz. And for this vehicle, the fundamental body bending frequency, here we are again concerned about that for guidance and control purposes. It's at 8 hertz, and then it gradually increases over time as the propellant mass is expelled. So we kind of sort of see that effect with that series of peaks. And so we look at this flight data, and we look for these body bending modes, and ideally they are difficult to find because ideally they never get excited in flight. But the fact is they do get excited in flight, and during certain time segments they may be excited to higher magnitude levels than at other times for a whole variety of reasons. So we may be interested in the amplitude shift as well, but mostly we're interested in the frequency shift. So that's some launch abort data, and you can download that from my blog. And another interesting thing is now I've shifted the time scale here, but this is actually still from our launch abort system pad abort test, and this is from I think it's from a different sensor. Let's see. So in this, yeah, these are from 2 different sensors. But at the end of motor burn of the launch abort motor, the main motor burn, we have another series of spectral peaks showing up in a Waterfall FFT plot. And this abort motor, it had its solid rocket motor cavity pressure oscillation, and this was during tail-off, and it started about 685 hertz, and then it swept downward to 670 hertz. And a conclusion was made that this resonance is considered to be a phenomenon of the low pressure end of burn gas dynamics of the reverse flow motor. So, and another thing you have to, of course, to realize to happen is the propellant is burning away, the acoustic cavity volume increases, and as that volume increases, then the acoustic pressure oscillation frequencies decrease. So that changes in opposite direction than the body bending frequency shift was. So again, this is we look for this sort of data when we're analyzing flight accelerometer data, and not all solid rocket motors have distinct thrust oscillations, but some do, and if they do, they can happen at during the ignition or during any time in motor burn up to and including the tail off. Okay, here's a solid rocket motor, and I'm not going to identify the model number because it gets into some ITAR sensitivities. That's dark gray here is a solid propellant. This is a cross section. These white organ pipe cavities here, these are where the combustion takes place. So we get, due to vortex shedding and other types of gas dynamic effects, we get standing pressure waves, oscillations occurring. And then that drives acceleration, and so the resulting structural boron vibration resulting from that propagates forward to the potentially to the critical avionics locations. So we need to understand the amplitudes and frequencies of these thrust oscillations that occur, if they do occur, so our avionics can be designed and tested accordingly. So this is a suborbital launch vehicle, is unmanned. This is a Waterfall FFT for a vehicle that had the motor on the previous slide. So again, we have magnitude, which is proportional to acceleration. We've got time in seconds and frequency in hertz. And this was actually a motor adapter bulkhead that was forward of the motor, and this is the longitudinal axis. So in this case, we see the pressure oscillation. It begins about 520 hertz there. And then over time, as mass is expelled, it sweeps downward to 450 hertz. So that's important to know for design and test purposes for avionics. There's another little sequence of peaks occurring at about 360 hertz, and I don't always know. Sometimes we just cannot identify what all the spectral peaks are due to. So was this due to some spurious noise or something else going on with the launch vehicle, or maybe the thrust vector control system? I wish I knew. Further investigation would be needed, but this was actually a long ago launch of this vehicle, so that opportunity has come and gone. So now we're going to look. This is actually another vehicle that had this same motor. Again, we have a Waterfall FFT, same motor adapter, bulkhead, longitudinal axis measurement location. And again, we see about 520 hertz sweeping down to about 450 hertz. Again, we do get some other smaller minor spectral peaks, and I wish I knew what those were. I don't. But I do know that this series, the main series of peaks there, sequence of peaks, that was due to the cavity oscillation, the thrust. Sometimes it's called a resonant burn or motor buzz or thrust oscillation. You'll hear those various terms applied. Okay, now we have a different solid rocket motor, and the particular characteristic of this was that upon its ignition and for a few seconds thereafter, it had a thrust oscillation or pressure oscillation that swept downward from 700 to 550 hertz. So that was an interesting effect that occurred. And this is not flight accelerometer data. Rather, it's from a static fire test. So for the static fire test, this vehicle was mounted essentially close to the ground, just maybe a foot or two above the ground. And it was horizontal. The longitudinal axis of the motor was horizontal with respect to the ground. And it was enclosed in a frame, a frame made of heavy-duty beams, so that the motor could be lit off, but it would just remain stationary, as mounted to it's called a test stand. It's mounted to the heavy-duty test stand. So during this static fire test, we had the opportunity to collect some accelerometer data. And this was on the forward dome of this particular motor, which, by the way, is not a very good place to mount avionics components, but for a variety of reasons, sometimes we're forced to do that. Maybe there's a thrust termination charge, for example, for the flight termination system. But anyways, we did get some very high levels on that forward motor dome, and those are shown in the waterfall plot here. They start about 700 hertz, sweep downward. For some geometrical reason of some sort, there's sort of a little jump here where it jumps down to 550 hertz. And that was due to some complex cavity geometry inside the motor. So again, avionics need to be designed and tested accordingly. And really a good way, when avionics components need to withstand these sorts of sinusoidal oscillation, a good engineering practice type solution is to mount them via isolator grommets, because the isolator grommets can do a wonderful job of filtering out this high frequency energy. And typically when we isolate avionics, the mounted isolation frequency might be down around 50 hertz, maybe as low as 20 hertz, which would be several octaves lower than this the frequencies shown here. And if that were the case, then we could just ignore this data. It would be unnecessary to test an isolated component for that particular sine sweep that occurs. But of course, we have to do some analysis to prove that, and we also need to do some testing to verify our isolator stiffness and make sure our isolators are linear, or how they what happens if they're at hot temperatures or cold temperatures, or do they bottom out? So designing and testing for isolators does require quite a bit of effort, but it's effort that pays a great dividend. We're going to shift away here. We've been doing some rockets type data, spacecraft type data, but now we're going to go to music. And some of you maybe have an Escher print in your office. Engineers really like this, and there's different types of prints. And this one is called ascending and descending. So it looks like those men that are going in a clockwise direction are continually ascending this staircase. They're always going upwards. And the men that are going counterclockwise, it looks like they're always stepping downward. Well, because Escher was really good at his drawings and he could create this sort of optical illusion, and made a series of famous prints. And what's interesting is musicians like Bach, in their own way, kind of picked on this theme as well. And Bach is actually wrote some pieces of music based on this principle where the tones appear to continually ascend or to descend, and he had some fun with that. And also there's something more just kind of synthesized called a shepherd tone that's related. So here's a shepherd tone, and we're actually going to look at it in terms of its Waterfall FFT. Now, if you'd like to generate your own shepherd tone or listen to an example, you can go to the Vibration Data blog. And in fact, I might just show you what we can do. If we go to Vibration Data and we pick up the GUI package here. So I've got something called a sound file editor. And what this editor will do, it'll allow you to generate some of your own sound files. So if we go to Generate Sound, we can, so far per version 1.1, we can generate just a pure sine or a beat frequency, or we can design a shepherd tone. When I say design, I mean really what I mean is synthesize. So if we synthesize a time history for a shepherd tone, we can choose. We got 2 sample rates to choose from. These are typical audio sample rate type numbers. We can choose the number of tones as well as their duration. And then once we've done that, we can export the data to a WAV file, which is a sound file, which we can then listen to. And we can also export the data to our Matlab workspace, so then we can do things like take a Waterfall FFT. So this is just a very quick introduction of how you could generate your own shepherd tone. You can play around with that, which I encourage you to do so. And let's see, what's kind of really going on with these shepherd tones? Well, in this one here, we're going to start off with a couple of tones. We're actually going to start with 3 tones. And the first is going to be at 50 hertz. And then we've got one at about 100 hertz or so. And, well, maybe that's more closer to 55, 110, 220 or so. But anyways, what happens is we have a logarithmic sweep rate, and as time goes on, we do a logarithmic sweep rate, and each of those 3 tones then sweeps upward. And in this case, the maximum frequency allowed is about 400 hertz. So let's look at this one that starts about 220, 225 hertz, whatever that is. It sweeps upward, and it reaches 400 hertz. Then it goes back to here, and we're gonna pick up with that tone. Again, the frequency is going to start off near 50 hertz or so, and then it's going to sweep upward and do another cycle going up to 400 hertz. Well, we have, let's see, the second one to reach the ending frequency is the one that started about 110 hertz or so. So it reaches its end, then this tone picks up again at a lower frequency down here, and then goes, and then so on. So you can see that each of these frequencies is rising, and when each of the tones reaches 400 hertz, it starts back up again at the low frequency, and so we could just produce this continuous series of upward sweeping tones, and that's somewhat the musical analogy of that Escher print that we saw earlier. So people like to play around with those. It's an interesting sine effect. It's interesting. The shepherd tone is more, just something that's it's made up. It's synthesized, but Bach and maybe some other composers picked up on this theme and put it in more of a musical form and did some pieces that are more beautiful to listen to, and the musical poetry effect. So anyways, the Waterfall FFT, it's really a fun tool to play around with. Anytime we have data where either the amplitude or frequency is changing with time, the Waterfall FFT is a real interesting way just to study what's going on. Now, some say if we just had steady-state random vibration, would we do a Waterfall FFT? No. If we had pure sine vibration at a steady-state amplitude, would we do a Waterfall FFT? No. But if we have these cases, which do occur sometimes in nature and sometimes in our rocket motors and our music, if we do have these cases where these parameters of frequency and amplitude change with time, it's a wonderful and fun tool to use. So if you're a college instructor, a university instructor, you're welcome to use these tools and the Vibration Data GUI package for your teaching and research. If you work in industry, you're welcome to use these tools in your industry for your work problems. And if you have any comments or questions, please send me an email. And that about wraps it up for our Waterfall FFT unit. And for our next webinar, we're going to look at, we have to revisit FFT magnitudes and figure out what happens when we take an FFT of white noise. So thanks for listening and participating, and goodbye for now.